Hi everyone. This is Miss Buchanan. This is our second to last notes. There's technically 3 weeks of school left, but this week and next week we're going to use it to learn about gases and gas laws. And then the final week, from what I understand, is possibly just going to be a time for those of you who don't have your work done that you can make up work. So no new work will be assigned on the third week. So we're going to talk about gases. Gases are very relevant. You can look at all the pictures here. We have a hot air balloon. We have airbags, just the earth, warm air rises, cold air sinks, and hot air balloons. So we're going to talk about a lot of stuff. So the importance of gases. This is one example, are airbags. If you didn't know this, the gas inside of your airbag is actually nitrogen. And the reason nitrogen is actually put into your airbag and not oxygen is because oxygen is flammable and nitrogen is not. So if you've ever been in a car accident and the airbag is inflated, the N2 is what inflates the bag. Now, if you've been in a car accident and your hands are anywhere near the steering wheel or certain parts of the airbag, sometimes you can come up with burns, and that's actually from the sodium. So this is sodium azide, and when sodium azide is actually reacts, it's a decomposition reaction, and it breaks down into sodium and nitrogen gas. Nitrogen gas is what we call an inert gas, and it means it does not react with other things. Nope, went too fast. So we're three states of matter: solids, liquids, gases. Gases are spaced far apart, and basically the gas particles are hitting the walls of the container. They're not hitting each other because there's no attraction between gases. However, they hit the walls of the container and they bounce back and forth. So the more particles in there, what would happen is you'd have more collisions with the walls of the container, and then therefore you would have an increased pressure. So general properties of gases. There's a lot of free space. Gases can be expanded infinitely, and the reason that is because there's a lot of space between the particles. Gases fill containers uniformly and completely, and then gases diffuse and mix rapidly. So gases can interact with each other. Air is a mixture, and it's a mixture of different gases. It's a mixture of nitrogen and oxygen, carbon dioxide. So gases can mix and not interact. Diffuse means to spread out. So if you've ever sprayed something in your room, or you've sprayed something in a room, you eventually will get that scent across the room because the gas particles are pushing it across the room. What is this? Pressure. Okay. Pressure of air is measured with a barometer. Now, we don't use barometers like this anymore, but we do use barometers, and barometers are filled with mercury. That will always happen. We will always use mercury in barometers because if we didn't, we'd have to have a really tall glass tube. And we have a shorter glass tube is because of the density of mercury. So mercury rises in a tube until the force of mercury balances the force of the atmosphere. So basically, if the pressure increases, it's going to, if you see here, if the pressure increases, it's going to push down on this mercury. It's going to push down on this mercury and then push the column up. If you have low pressure, what it means is you're going to have a rise in the bowl of mercury here, and then the column is going to shrink. So mercury rises in a tube until the force of mercury balances the force of the atmosphere. Just like a straw in a soft drink container. It's just like your body. Your body doesn't collapse upon itself because the pressure inside your body is equal to the pressure outside your body. So how do we measure pressure? We can measure it in many different forms. Pressure is important when we talk about weather. So if we have a cold front coming in, usually the pressure drops. The more the pressure drops, what's that saying is the bigger there is of an air system coming in. So a bigger storm. Actually, meteorologists actually use it to predict the size of a hurricane. So if they see that the pressure's dropping a lot, then what will happen is if the pressure drops a lot, you will create a much bigger storm. So that's what they watch for. So there's a few different ways that we measure pressure. One is in standard atmospheres. So 1 ATM. So standard pressure is 1 ATM, or it's called 760 mmHg, or it's called torr, named after Torricelli, who is the Italian gentleman who discovered a barometer and measured air pressure. Is also 29.92 inches of mercury, 14.7 pounds per square inch. We use that in the United States. We'll use that to measure tire pressure. Or 101.3 kPa. PA means Pascal, and the K in front of it means kilopascal. And it's also about 34 feet of water. So 1 ATM is equal to about 34 feet of water. Down here it says memorize these. You don't, you're not in class. So you can use these, and we're going to use these for pressure conversions. So for example, if I give you a number in atmospheres and convert it to torr, I'm going to show you how to do that. So you don't need to memorize these. Just have these written down in your notebook or close by so you can use them for your homework. So let's look at a couple of things here when we talk about pressure conversions. So what is 475 millimeters of mercury expressed in ATM? We're going to go back and use the factor label method. We're going to start with 475 mmHg. Now, I'm going to go back here. And what is the relationship between mmHg and atmospheres? Well, 1 ATM is equal to 760 mmHg. Okay, so 475 mmHg. I'm putting 760 mmHg on the bottom. Why? Because I want the mmHgs to cancel out. And I'm going to put 1 ATM on top because that's what I want to be left with. And when I do that, I am left. So I'm going to divide 475 by 760. And I'm going to make that 0.625 ATM. Letter B. The pressure of a tire is measured at 29.4 psi. What is this pressure in mmHg? Well, if I have 29.4 psi, I am going to put 29.4 psi on top. That's what I'm going to keep. And then on the bottom, I am going to put 14.7 psi on the bottom and put 1 mmHg on top because I want the psi to cancel out. So this cancels out. I have 760 mmHg. So what I'm going to do here is I'm going to do 29.4 psi, divide by 14.7, and multiply by 760. Now, we're going to go back and talk about sig figs a little bit. There are 3 significant figures in 29.4. That's what we're going to use. We're always going to use this starting number up here and here as your sig figs to figure out your sig figs. So what's my answer going to be? 1.52 times 10 to the third mmHg. So you're going to take 29.4, divide by 14.7 times 760. So it's like 1,000. If you get in your calculator 1,520, it's the same as 1.52 times 10 to the third. Okay? So this is page 1 in your homework packet. So I wanted to transition over here so I could show you some examples about how to set up these problems. I will do a couple of them, and then what I want you to do for practice is I want you to actually do the rest of them and then check your answers when I put them on Google Classroom. So if I am going to start with 98,745 PAs, so 98,745 pascals. Okay. I apologize for the handwriting. And I want to convert it to ATM. So if you look up here, 1 ATM is equal to 101,300 PAs. So what I'm going to do is I'm going to put 101,300 pascals on the bottom because I want pascals to cancel out. So I'm going to pick another color here, blue, and I'm going to put a line through pascals. And then what I'm going to do is I am going to put 1 ATM on top. Okay, so 98,745 PAs. So I'm going to take that, I'm going to divide that 98,745 divided by 101,300,000, and that gives me 0. 1, 2, 3, 4, 5, 6 figs. So 0.97478 ATM. Okay, so next one, it says how many millimeters of mercury are in 31.88 inches of mercury. So if I look here, I have 760 mmHg, and it's really is equal to 29.92 inches of mercury. So what I'm going to do is I'm going to go oops, went too quick. I'm going to do 31.88 inches of mercury, and I'm going to multiply, and I'm going to put that so right here, and then on the bottom I'm going to put 29.92 inches of mercury on the bottom. And then I'm going to put 760 mmHg on top. Okay. So I'm going to cross this out. So I'm going to say 30. So now I'm going to do the math. So I'm going to do 31.88 divided by 29.92 times 760. So I'm going to say it's going to be equal to 810 millimeters of mercury. Okay, so that's the setup on how to do pressure conversions. So now I'm going to move to gas laws. So the first gas law we're going to talk about is Robert Boyle. Robert Boyle was a scientist, and he that's all he worked was gases. But Robert Boyle was from Ireland, and Boyle's law says pressure. So when we think about pressure and volume, we're looking at the two things between, like, the relationship between pressure and volume. So if you think about this, so if I increase the pressure on something, what's going to happen to the volume? Well, Think about that. So if I increase the pressure, so if I take a balloon and I blow it up, but then I squeeze it and I squeeze on the outside of it and push it in, what am I doing to the volume? Well, I'm decreasing the volume. So that would be what we call an indirect relationship. So as pressure increases, the volume will decrease. Or as volume increases, the pressure will decrease. So this means pressure and volume are inversely proportional. So things you got to think about here. So we're only looking at pressure and volume. Moles and temperature are held constant, which means they do not change. So for example, pressure goes up as volume goes down. So the equation for Boyle's law is P1V1 is equal to P2V2. Couple things to think about when you set up these problems. First, the ones mean initial, the seconds mean final, okay? That's one. The other thing is you need to make sure your units are the same on both sides. So for example, if I start with ATM, I'm going to end with ATM. If I'm going to start with milliliters, I'm going to end with milliliters. But your units need to be similar on both sides, okay? Hopefully my animation will work here, but it just shows pressure and volume are inversely proportional to each other. We're going to move along. So Boyle's law, a bicycle pump is a good example of Boyle's law. As the volume of the air trapped in the pump is reduced, its pressure goes up. So if you ever actually used a manual bicycle pump, as you push down, it gets harder to push. And it's because the volume is decreasing, so the pressure is increasing. So if you notice here, I have 1 ATM, the volume is 1 liter. I have 2 ATM, my volume was cut in half. And if I have 4 ATM, my volume was cut in half again, and the temperature all remained constant. I will show you some example problems for each of these. Next is Charles' law. I'm going to try to get through this a little quicker. Charles' law has to do with volume and temperature. So temperature and volume and temperature, it means pressure is held constant and moles of gas are held constant. So this is Jacques Charles. He isolated boron and studied gases. He was actually someone who he was what they call a balloonist. He would go up in hot air balloons. So volume and temperature are indirectly proportional. So what does that mean? And you can think about, we see this happen all the time. If you have a basketball sitting outside and there's a season change and it gets cold, as the temperature goes down, so will the volume. Another scenario is if you heat something up. So as the temperature goes up, the volume will go up. So they're directly proportional. Now, there's one thing we need to talk about here about temperature. Temperature, when we talk about temperature and gas law problems, temperature has to be converted to Kelvin. And how do you convert temperature to Kelvin? Well, you take degrees C. You take, let's see if I can draw it on here. I should be able to take, that's not drawing, but anyway, you take your degrees Celsius and add 273 to it. So degrees Celsius plus 273 will give you the temperature in Kelvin. And you're like, why do I have to do that? Well, Kelvin has a direct relationship to kinetic energy. Okay, so as kinetic energy goes up, temperature goes up. So we have to change Celsius to Kelvin to show that relationship. If you keep your temperature in Celsius, your problems will be incorrect. Now you can convert them back, but when you're doing the work, they have to be in Kelvin. Okay. So this is the original hot air balloon, pretty nifty. And then this is just an animation that should have worked, but if you if you heat up the syringe, so what's going to happen when you heat up the syringe, the particles in there, as the temperature increases, the volume is going to increase. Okay, actually, I'm going to stop for a minute. I'm going to switch to another slide. Okay, so Charles' law problem, I'll go back and show you a Boyle's law problem, but I wanted to show you a Charles' law problem because I wanted to emphasize this, where I talked about just a moment ago that Kelvin is equal to C plus 273. Celsius always has to be changed to Kelvin. So if I look at here and I said a sample of ammonia occupies a volume of 750 milliliters. So I'm going to put this here. So that's 750 ml, and that's just fine. You don't need to convert it to liters. And I have a temperature of 22.5 degrees C. So if I take 22.5 and I add 273 to it, this is going to be 295.5. Okay. Okay. Volume. I'm going to actually, I have to, volume you have to calculate. Temperature is what volume will it occupy at 75 degrees C. So again, we're going to use this equation up here, and we're going to take 75 plus 273, and it's going to be 348 K. Okay, so let's talk about this for a minute. Did the temperature go up or down? Well, we went from 22.5 degrees Celsius to 75. So it definitely went up. So think about the relationship. As temperature goes up, what's going to happen to your volume? Well, your volume is going to go up. So let's use this equation right here. V1 over T1 is equal to V2 over T2. So volume 1 is 750 ml divided by 295.5 Kelvin is equal to V2. And my temperature here is 348 K. So how do we solve for V2? Well, we have to isolate the variable. We have to get V2 by itself. So I'm going to multiply both sides by 348K. Okay, and I'm going to multiply it over here. So K cancels out. And so I'm going to take 348 times 750, and I'm going to divide by 295.5, and you will get an answer in, should be in 2 sig figs because you have 750. So I'm going to say it's going to be 880. If K cancels, it's going to be 880 ml. Okay. So the last law we're going to talk about today. I know it says Gay-Lussac. His actual name is Guy. It's French. If N and V are constant, so N stands for moles and V is volume, if they're constant, then pressure and temperature are directly proportional to each other. So what that's saying is as the temperature increases, so will the pressure. So if the temperature goes up, pressure will go up. If temperature goes down, pressure will go down. Okay, now and you can even think of it this way. If pressure increases, temperature is going to go up. And the reason that's going to happen is because there's going to be more collisions. The more collisions with the walls of the container creates more friction. More friction causes more heat. Gay-Lussac's pressure and temperature. So as temperature increases, so does the pressure. Temperature cannot be 0 or negative. Well, let's talk about that really quick. If you have a temperature of 0 Kelvin, what that means is there's no kinetic energy. Well, if there's no kinetic energy, there's no life. So that's why temperature cannot be 0 or negative. Cannot divide by 0 or have a temperature be. You cannot have, yes, you cannot have 0. Because if you have 0 Kelvin, that's absolute K, and that means there's no kinetic energy. So this is, remember to convert all your temperatures into Kelvin. A sample of neon has a pressure of 2 atm and decreases to 1 atm. So I have a pressure of 2, and I go down in pressure. So did the pressure go up or down? It went down. Okay? If the gas's temperature starts at 0, okay? If the gas's temperature starts at 0, so 0 plus 273. Now I said up here you cannot have the temperature cannot be 0. It cannot be 0 Kelvin, but it can be 0 Celsius. So 0 plus 273 is 273 K. Okay? So pressure is going down, so temperature goes down. That's what we can expect to happen. So let's see if it does. So P1 is 2.0. And that's going to be 2.0 atm. You're going to notice I'm going to keep my units here because I want to show you how they cancel out if I can write my units. So the equation is P1 over T1. So that's 273K is equal to 1.2 atm. Over T2. So you're solving for T2. Well, where's T2 at? T2 is in the denominator, which is not the best, but we can figure it out. So if I want to, first of all, I want to isolate the variable. So what I'm going to do is I'm going to divide both sides by 1.2 atm. It's going to be a 1 on top. So if I divide, then this will be 1.2 atm. Okay, so if I need to fix that, so what I'm going to do first is I'm going to cross out the units. That cancels out. So now I have 1 over T2 is equal to 2.0 divided by 1.2 times 273. Okay, so let's flip that. What do you mean by that? Well, whatever I do to one side, I got to do the other. So in order to get T2 in the numerator, I got to flip it. So what I'm saying is I'm going to take 1.2 atm, and I'm going to multiply it by 273. Divide by 2 atm. And that's going to be equal to T2. So I'm going to cross out that. So 1.2 times 273 divided by 2.0. That gives me a temperature of 163, so approximately with 2 sig figs, 160 Kelvin. Well, do you expect the temperature to go up or down? I expect to go down, and it did. It went from 273 to 160. Did the change in the temperature indeed act as you predicted? Yes. So I'm at the end of the notes. There are a couple gas law problems, practice problems. If you go through the slideshow, and I will actually upload the slideshow to your assignment so you can go through that. I'm only doing pressure changes and the 3 gas laws this week. I just want you to practice on the homework practice. I'm not having an objective check this week. I'm just going to have one big objective check next week with the other stuff that you learned. Actually, let me retract that. I'm going to think that over. You will have a gas law lab to do. It's through Flynn Scientific. There's a sheet. You'll need to turn that in. I will keep you posted, or I'll actually put it in the instructions about an objective check over the 3 gas laws and pressure changes. And then next week, we'll learn ideal gas law, and one other law, and then we will be finished. And hopefully we will be finished with online school for a very long time. I hope you all have a wonderful week, and I will talk to you during Google Meets. Have a great day.